We were talking about calculations and significant figures, and we talked about subtraction and addition last, and then we talked about rounding. I accidentally backed up through some of these slides. So let's do some examples, and I forgot to get the calculator out. Cell phone calculator works in a pinch, but the real calculator is better. So perform the following calculations. Round the answers to the correct number of significant figures. So the thing to do is just do the math and write down the number first. So here we have 45,900 meters plus 10.49 meters. So we do that on the calculator. Calculator says 45910.49 meters. If there's a unit, always write down the unit. Now, to round this, we need to think about what operation are we doing. We're doing addition. So the rule for addition is we're looking at decimal places, not number of sig figs. So 10.49 has how many decimal places? It's got 2. How many decimal places does 45,900 have? Well, it doesn't really have any decimal places. Well, where's the uncertainty in this number? We might say the last digit, but are these significant figures, these trailing zeros here? No. Trailing zeros at the end with no written decimal point. Those are ambiguous, and so we're going to assume the worst case scenario and say that they're not significant, that they're holding the place. And that puts the uncertainty in the hundreds place. Okay? The uncertainty in 10.49 is in that last significant figure, 10.49. So we have hundredths and we've got hundreds. So really what we're looking at is which one has the greater uncertainty? This one has the larger uncertainty. This is going to limit the answer. And so we're going to have uncertainty in the hundreds place, which is right here. We need to be careful when we round that number because 459 is not going to be a good answer. So we should call this 4.59. Oh, that's just not even going to fit there. 4.59 times 10 to the 1, 2, 3, 4 meters. I guess I'm moving this decimal point 1, 2, 3, 4 places. I've got an exponent of 4, big number, positive exponent. The uncertainty is in this decimal place. Any questions? Does it bother anyone that we added something to 45,900 and our answer is still 45,900? Does that bother you? A little bit maybe? Like, well, that doesn't seem right. But if this is a measurement of distance to the nearest 100 meters, does adding 10 meters matter at all? No, it doesn't. It's not significant because the original, the 45,900 is not known that closely. It's like having a semi-truck full of, I don't know, 10 ping pong balls. Okay, and you've got like 1 million ping pong balls in there, and you throw one more in. Is that really going to change the mass of the truck significantly? No, it just doesn't really matter. Let's do this next one. 29,412 divided by 5.10 times 10 to the third. So my calculator is telling me 5.767058824. And what would the unit on that be? No units. Units act like variables. They cancel out. Milliliters divided by milliliters. They're gone. Now, if you did not get this number, you're probably not communicating well with your calculator. When we enter a number in scientific notation in our calculator, we want to use the EE button, or some calculators have an EXP button. And both of those buttons stand for times 10 to the. So you go 5.10 and you press EE or EXP and you say times 10 to the, and then you press the 3. And we do use scientific notation throughout the course. Sometimes you can avoid it, but when we use Avogadro's number, there's no avoiding it. And so we have to learn how to use scientific notation on our calculator. If you have issues with that, please talk to me and we'll get that straightened out. How many significant figures should my result have? 3. This is division. So we count the number of sig figs in the numerator. There's 5. And the number in the denominator is 3. Smaller number wins. So we're going to round this to 3 sig figs. And we're going to report this as 5.77. Writing down the whole answer first is a good step. Okay, because then if you rounded incorrectly and realized, oh, wait a minute, I was supposed to have 5 significant figures, you wouldn't have to calculate it over again. You just have to round it differently. If you round it off too much and don't write down the original answer, then you have to do the whole thing over again. So when in doubt, leave too many significant figures. It's easier to fix. Okay, number 3. Let me zoom in on this so I can see it. 16.3521 minus 1.448. You need to press the equal sign to tell your calculator, yes, I want you to finish that subtraction before you divide by 7.085 equals. I love the sound of all the calculator buttons going. 2.10 3613267. Units. Centimeters. Here we've got centimeters squared minus centimeters squared. So the numerator is centimeters squared. We're dividing by centimeters, so that cancels out one of them. Now, like I said Tuesday, if you think I've got the wrong number as my answer, please just yell at me, because I do it. And I'd like to pretend that I do it on purpose to see if you're paying attention, but that's not the truth. That's just not true at all. How do we figure out how many sig figs here? We've got subtracting and dividing. We need to look at both parts to see what's going on. So this part up here, the numerator, if we did that by itself, let me do it again real quick, 1.448. The result of that is 14.9041 square centimeters. That's subtracting. Here we have 4 decimal places. Here we have 3. So this result here would have 3 decimal places. If that was our final answer, we'd round it to that 4. It's not our final answer, so we don't want to round it yet, but we need to observe how many significant figures it has, because this is the number that's in the numerator. It has 1, 2, 3, 4, 5 significant figures. The number in the denominator has how many? 4. So 4 wins. And we'll round this. We got 1, 2, 3, 4. That's our uncertain digit. The next one's 5 or greater. We're going to round up. So this will be 2.104 centimeters. Any questions? I'm sorry about the giant units on there. It did weird things to me, and I decided that it wasn't worth the time trying to straighten that out. So number 4. So we have 4.8. So I'm going to enter that as 4.8 EE4 times 1 divided by 1,000. And that's then divided by 11.55. And the calculator, again, gives me way too many digits. Next, let's look at the units. What's happening up here with the milligrams? They're going to cancel out. And so in the numerator we have grams. In the denominator we have cubic centimeters. So this is going to be grams per cubic centimeter. We don't have any adding or subtracting here, so that makes it a little easier. How many sig figs in this number? 3. How many in this number? Pardon me? Unlimited. This is a conversion factor. 1,000 milligrams to 1 gram. That's a metric conversion factor. That's a definition. That is an exact number because we decided that a gram was 1,000 milligrams. So we don't have to think about those guys. And then how many in the bottom? 4. So 3 is the smallest. So we're going to keep the 4, the 1, and the first 5. And that'll end up being 4.16 grams per cubic centimeter. Any questions? Accuracy and precision. These are words that have a similar general meaning, and yet there's a difference to them as well. Accuracy refers to how close the measured value is to the actual value or the true value. Precision tells us how close a series of measurements are to one another, or how reproducible they are. You can have accuracy and precision, or you can have accuracy without precision. You can have precision without accuracy, and then you can have measurements that have neither accuracy nor precision. Here is an example of 3 students repeatedly weighing a lead block, and the accepted or true mass of this is 10.00 grams. So they're each doing 4 trials. We often do multiple trials because there's error in any measurement, and some of it is random. And random error can be gotten rid of by doing multiple trials because it averages out. So here we've got 10.49, 9.79, 9.92, 10.31, and then the average is 10.13. We can look at these averages and which one of them is closest to 10.00. Student C, right? This is closest to the true mass, so this is the most accurate measurement. It's a little harder just looking at these numbers to tell which one is the most precise. A lot of times it's helpful to graph things because it makes it visual. So here are the results for student A. The true mass is shown as the blue line. His average is the pink line, and these are the different measurements that they made. He made, she made. I don't know. We'll just decide they're all guys. I don't know why. So is this a very precise set of measurements? Are these really close together? No, they're all over the place. So this is imprecise. And then we look at the average, 10.13 compared to this, that's not very good. So this student was inaccurate and imprecise. Over here, this student, all of the results are close together, but they're all too low. So this student was precise but inaccurate. And this student wins the prize. The actual value and the average are very close together, and all the values that were measured are very close together. That's accuracy and precision. Usually accuracy and precision go together. If you have precision, generally that indicates that you're more likely to be accurate, but not always, because student B was precise but not accurate. So student A was inaccurate and imprecise. Random error is error that has an equal probability of being too high or too low. So sometimes it's high, sometimes it's low. And because of that, we can average multiple results and reduce that random error. That's probably the case with student A, that there's a lot of random error. Student B has a precise result, meaning there's very little random error. We don't see a lot of spread in the data, but it's inaccurate, and that suggests a systematic error. A systematic error is going to tend in one direction or the other, too high or too low. If you're weighing apples at the store, and every time you weigh them, you have your thumb on the scale, all your weights are going to be too high, right? Because you've got the mass of your thumb pressing down on the scale. That's an example of a systematic error. Or if the measuring device that you're using isn't calibrated correctly, it's always going to be off in the same direction. There's a lot of different possibilities for systematic error. And then student C has little systematic error or random error, both accurate and precise. Any questions about that?